Good day. This is a short video on amortized analysis, part of the series of videos on advanced algorithms. And in this video, we'll look at a very simple example, which is the last exercise of lecture 5 in the course, which is inspired by exercise 17.3-7 from CLRS textbook. So the exercise asks to implement a dynamic multi-set data structure, or a bag data structure that has these two operations. One is insert X into S to this multi-set. Multi-set means that we can have several copies of the same element in the set. And then delete larger half just deletes the largest half of the elements from the set S and prints them out. And so specifically it deletes size of S divided by 2, the ceiling of that, this number of elements. So the goal is to implement this data structure so that any sequence of M operations run in big O of M time, worst case. In other words, what we want is that the amortized cost of any of these operations is a big O of 1, is constant. So how do we do that? So the exercise formulation at the end of lecture 5 gives some hints what we want to do. First, it says to achieve that, what you want is you want to implement delete larger than half operation so that it runs in linear time with respect to the size of S. So first, let's look how we can do the amortized analysis, assuming that we can implement delete larger than half in linear time. So to implement this data structure, we simply have an array S with num as the counter of the current counter of how many elements we have in the array. So the size of the array may be larger. Let's initially assume that the array is very large, so we don't have to care about reallocating like in the dynamic table example from the course. And then let's say we can implement delete larger than half in linear time using this median linear time implementation of the median algorithm, which finds the element that is in the middle if the array was sorted, without actually sorting the array. We can say a few words later about how we actually do this implementation. But let's assume we can do the implementation of delete larger than half in linear time. Then the analysis, amortized analysis, is quite simple. The intuitive way to do that is to use the accounting method. Let's say I pay $3 for the insertion. So it costs $3. I use $1 to actually insert an element. And then I put $2 into the account associated with that element. So at some stage in the algorithm, after, let's say I have inserted 8 elements, there will be 8 elements in the array, and each element will have $2 associated with it in its account. Then we can do any sequence of delete larger than halves for free. So let's do one delete larger than half. It costs linear in terms of the size of S, of how many, in terms of how many elements there are in the array. So I will use $1 from each of the elements to pay for delete larger than half. So I will use $1 from each of the elements. So we'll be left with just $1 on all of the elements. That will pay for delete larger than half. And then this delete larger than half will actually get rid of all of these elements. We'll print them out, remove them from the array, decrease the num counter. So they may be, obviously the elements can be anywhere in the array. They are not sorted, so it will pick out the necessary elements, rearrange the others, and print out the ones that are removed, and we'll do all that in linear time. And then instead of just throwing this money away for the removed elements, we take and put all the dollars from these elements into the accounts of their friends remaining in the array. And because we are removing half of the elements, actually possibly exactly the same number as remains in the array, or maybe one element more than remains in the array, it will be enough dollars in the elements that we remove so that every one of the remaining elements receives one additional dollar, and we have again $2 in the accounts of all of these remaining elements. So after I have done delete larger than half, I end up with the same invariant that every element in the array has $2 in the account, so I can do as many delete larger than halves after that as I want, or I can do some inserts and so on. So here we demonstrated that we can, the amortized cost of insert and delete larger than half is constant. Now, if we have also to take care of expanding and contracting this table and allocating and deallocating as we do that, and copying elements as we reallocate the table, we can have, on top of this analysis, we can have the analysis that we did for the dynamic table in the course, and everything together will also work. You can try to think about that as an exercise. How does the full amortized analysis works if we also add the cost of expansion and contraction of the table? So how do we implement delete larger than half in linear time using this linear time median algorithm? It is quite simple, but at the same time you have to take care of details. So this is a simple implementation that is not exactly correct, and we will talk about that. So obviously you first take, so what is the x such that half of the elements are smaller than it and half of the elements are larger or equal than it. Then you can go through all of the elements in the array and see if the element has to be left. You copy it to the beginning of the array, so j goes from 1, and it's incremented whenever you leave the element in the array. Whenever you skip an element in the array, you increment I, but you do not do anything with j. So you have 2 pointers i and j going in the array. You take elements from position I that you want to keep in the array, those are smaller than x, and you copy them to the position j, so that after you go through the array at the beginning, starting from 1 to j minus 1 inclusive, you have all the elements compacted in the array that you want to leave. So that would be a linear time implementation. The problem is that if you have a lot of elements in the array that are equal to each other, and then you may end up removing too many elements here. So you want to remove exactly half of the elements from the array, so it may be that you want to remove only some of the elements that are equal to x in addition to all the elements that are smaller than x, but only some of them, just enough so that exactly half of the elements remain. So then the pseudocode gets a little bit more complicated. You can find it in the solution that are posted on the course Moodle page. Another interesting thing to think about is how or whether the exercise would change if I change this into deleting not largest half, but let's say deleting larger third or larger fourth or larger 10% of the elements. So try to think if you can extend the amortized analysis to show actually that still this is possible. You can show that the amortized cost of these operations would still be constant even if I remove some other fraction of elements from S. But it would not be constant if I remove some constant number of elements from S. Say, delete 100 largest elements. Then you cannot show that these operations can be implemented in constant amortized cost.